Hi everyone, this is the second introduction to chapter 5. We are going to talk about a concept named the current density, then the electrical resistance, and the electrical resistivity. So let's start with the current density. So the current density is simply the amount of current per unit area. So I divided by area. And as I mentioned in the previous video, when I'm talking about the current, 99% of the time I'm talking about the instantaneous current. So dq divided by dt, all right? So the rate of change in the charge with respect to time. Here we have 1 divided by A, the area. Now I'm not sure if I mentioned it in the previous video. The unit for the current is the ampere. It is uppercase A. And basically, the current density is in ampere divided by meter square. And make sure to not confuse the A over here with the area. This one is the area, and the A over here, which is the ampere. This one is a unit, this one is the area, it's a variable, all right? So the unit for the current density, ampere divided by meter square. All right, so let's look at the resistance. We seen in the previous video that when charge are moving in a conductor, there is some resistance and they are losing energy. This loss in energy is related to a drop in voltage. Now the resistance link the drop in voltage with the current. So basically the resistance in ohms, so the unit for the resistance is the ohm. You've probably seen it in your electrical course in high school. So resistance is equal to the drop in voltage divided by the current. Now just to give you an idea, when we're talking about the drop in voltage, let's imagine that we have 5 volt on one side of a resistance and we have 1 volt on the other side of the resistance. The drop in voltage delta V over here will be 4, so it's 5 minus 1. All right. Another point that is important, we are going to start building and making diagram about electrical circuit. This symbol over here is the symbol of the battery or the power source, and generally it has a bigger bar which represent the positive side. It has a smaller bar which represent the minus sign. This kind of zigzag represent the resistance. Now we are going to be solving again a lot of example. I'm gonna re-explain this in each example. All right. Last part is the resistivity. So let's say we have a copper wire. Even though that copper is a very good conductor, there's still some energy loss inside the wire. And if we want to predict in advance what will be the resistance of a given wire or any piece of equipment, we can link to the resistance to a value that we call the resistivity. That one is unique to each material. So copper has its own resistivity, silver, gold, and so on, multiplied by the length of the wire divided by the cross-sectional area. So the longer the wire is, the higher the resistance. The bigger the cross-sectional area is, the less resistance there is. And it kind of makes sense. The bigger it is, the easier the electron will flow in. The longer it is, well, the more energy it might lose. All right? So resistance equal resistivity multiplied by the length of the conductor we are considering divided by the area, the cross-sectional area. All right, so we are going to do one last video on the introduction, and then we are going to switch to some examples just to make sense of all of this. All right, so see you in the next video.